All right, we're live now, I think. We have sound. Yep, video, good. All right, so sorry I forgot to start this on time. So we're trying to find the area of a sector because we're trying to figure out how to integrate to find an area. So we're not quite at integration yet, but we're getting there. We've got some function, r, function of theta. And if we zoom in on it and take a little chunk of angle, call that d theta, essentially what we have is a sector of a circle. And we set up this ratio and proportion system, part over whole. Angle is d theta over 2 pi. The area is the sector over pi r squared. And if we solve that for the sector, what do we get? Pi's divide out, right? We got a 1/2 in there. We have an r squared in there. And we should have a d theta in there, right? Okay, so what that is just one of these little chunks. Now the d theta is getting small. We're thinking of that as the limit of delta theta, right? And so if we integrate this right here, that's going to give us the area inside a polar curve, okay? Because we have a whole bunch of these little sectors that we're adding up. Okay, so that leads to the polar area formula. Polar area. And so the polar area, again, it's going to be the integral as theta goes from some angle alpha to some angle beta. Right? So we have a totally different interpretation of the boundaries of 1/2 r squared d theta. And so we're going to try to apply that formula to our three-petaled flower. R equals the cosine of 3 theta. That's our next step. So that picture again, here's the pole and the positive x-axis. It starts with theta equals 0, r equals 1, and then loops around something like that. Hey, that's pretty good. So the maximum radius we get out here is r equals 1. And we found that happened when theta was equal to 0. Where else did we find that happened? At pi over 3 and 2 pi over 3. So here, r was actually -1. Theta was pi over 3. And up here, I think we're still okay. This is r is +1 when theta was 2 pi over 3. And then this thing completes itself. It closes off also when theta is equal to pi. So we found that that was the period of this graph also. And so you got to remember, periods of polar functions are not what you think they're going to be. It's not like periods of rectangular functions, Cartesian functions. You got to kind of play around. Yeah, there are rules for them, and the more you see the graphs, like we were starting to find those rules playing around at the end of class the other day. We'll take a look at those again in a minute. Depending on what number you multiply in here, you can tell what the period's going to be ahead of time. But not until you've done it a few times, and that's the problem. All right, so let's see. You see some symmetry in this graph right here? So there's 3 identical petals. Now one problem is if I start with theta equals 0, I get half of a petal if I go to pi over 6. I don't quite get a full petal. If I wanted a full petal, I'd have to do something like here, go from pi over 6 to, let's see, what was that next 0? Pi over 2. So I have a couple options here. Yeah, so we could find this second petal here because we have a whole thing starting at pi over 6 going to pi over 2. Or we could say that we could just go from 0 to pi over 6 and say we get half of a petal and we need 6 halves. Yeah, multiply by 2 and then by 3. So we got a lot of options. So that one sounds the easiest to me. As sure as I'm okay about the symmetry, and as I was graphing, I did see a lot of symmetry. So for example, I found a point right there and a symmetric point right there when I finished up, and they were balanced in terms of their radius and angle. So I'm pretty comfortable with that. So I think we're going to go with this one. We're going to go from theta equals 0 to theta equals pi over 6, and then we'll have to take 6 times that integral. Okay? Let's do it. So we want 6 times the integral as theta goes from 0 to pi over 6. Integral is 1/2 times the cosine squared of 3 theta d theta. Okay, so this isn't really a class on integration, although we use it a lot. So we've got a few options here. We could make believe we're on Calc 2 and we could find an identity to reduce this, or we could use the table in the book, or we could use a computer algebra system like Wolfram Alpha. Zach, what do you want to do? You're doing it on paper? Okay, keep going then. Might as well exercise our brains. No, the radius is cosine of 3 theta. The reason I drew those, I drew those one, oops, wrong button. Yeah, so R in this case is cosine of 3 theta. The reason I put the ones in there, I was just kind of curious about the maximum distance out we ended up being. What's that? Yeah, we can call it whatever we want, yeah. So we have to evaluate that integral right there. So what do we know that the, let's see. So cosine squared of x is equal to, let's see, is it? I thought it was 1 plus the sine. Well, no, I don't want to do another square. I want to do a angle reducing formula. So I think it's called the half angle formula. So that would be the sine of, let's see, I think this is going to be 2x all over, no, that's a cosine there. All over 2. Can I see a trig cheat sheet just to double check that? Did I write that correctly? Cosine squared is 1 plus the cosine of 2x over all over 2. Yeah, that's right. Okay, so we don't have an x here. What do we have? We have a 3 theta, so we're just going to replace x with 3 theta. So that means I'm going to have 2 times 3 theta, or 6 theta here. So this would be what you're going to substitute in to make that happen. So I'm going to start rewriting that. Let's see. So that's what I have so far for the antiderivative. Okay. From the book table, yeah. Yeah, so the books, the standard method that the book table comes from is this substitution. So it should match. All right, so we have to evaluate the endpoints, pi over 6 and 0. So what do we get there? So that's going to give me 3 times pi over 6 plus 1/6 times the sine of 0. Or no, sine of pi, sorry. Minus 0 plus 1/6 times the sine of 0. It's the sine of pi and the sine of 0. They are both 0. That's good. So this whole thing has gone to 0. And that's gone to 0. So that gives me 3 times pi over 6 times 1/2. So the 3's go in. Pi over 4 seems to be the area of all 3 leaves. Leaves, leaves, leaves. Petals, petals, there we go, petals. So that would be units squared, whatever the units are. And that seems to be the area of all 3 petals. Okay, so what can we do to check that answer out? We have a few options. Yeah, we could use the calculator. So the calculator could approximate this. Now, one thing that depends on is my integral right in the first place? Right, so that's a whole nother thing. So we'll double check that too. So did I even set this up right? Okay, well, I've got the area formula. 1/2 times the radius squared is what we're integrating. Our radius is cosine of 3 theta. All right, I'm pretty sure I got that part right. So then we need some kind of really the only way to check it is some kind of numerical device. So you could use the calculator or Wolfram alpha. You guys try the calculator. I'm going to try Wolfram alpha. How do you do them on the calculator? Alpha window. And oh, mine does not. Oh yeah, FN int, that's it. Okay, so I want to go from 0 to pi over 6. Oops, that's E. Pi, there we go. And my integrand is, let's see, 1/2 of 6. I'm just going to call it 3 times the cosine of 3, we can call it 3 whatever. I guess you got that? 3 theta d theta. Oops, I forgot to square my cosine. I think I do that right there. Enter. Yep, that looks like pi over 4 to me. Okay. Oh shit, I forgot to divide by. I hate when I do that. There we go. Yep, it worked out. Wolfram alpha is kind of nice because you can double check antiderivatives. So if I take integral of, I know, I have that. It's nice. cosine of 3x squared. 3x, cosine of 3x then squared, yeah. Yeah, I thought it was, how much did you pay? I had $3 sounds right, yeah. They said 30 for a minute. I was like, oh shit, that's a lot. Yeah. Yeah. So Wolfram alpha has a similar antiderivative. You can actually give it boundaries too. Like if I put the whole thing in here, if I do integral parentheses 3 times the cosine of 3x squared, comma x, comma 0, comma pi over 6, it should numerically evaluate it. Look at that. It even thinks it's pi over 4 exactly. Isn't that nice? Okay. Yep. Ooh, and it even gives me a Taylor expansion, partly. Oh, left Riemann sums with the limit. That's not Taylor expansion, sorry. Cool. Taylor expansion on this one would not be pretty. All right, let's do another one. How about, oh, this is a good one to look at. So I skipped derivatives and jumped right to integrals. Did you guys wonder why? Or you just thought it was? Yeah, it turns out they're harder. So we looked at area by looking at sectors of a circle instead of rectangles. And that made sense to me because we're sweeping out an angle. Okay. So the next question is, what the hell does a derivative mean? So what is a derivative in polar? Okay. Well, before we get to what it means in polar, what does it mean to you before we were in polar? What does a derivative tell you before? Tell us like tangent line slope, right? Okay. So I'm just going to make a note of that. Previously, in Calc 3, we did dy dx, which is slope of a tangent line at the point. Slope. In general, it gives us a slope function that tells how the rate of change of the function, instantaneous rate of change. So then the question is, okay, well, what if I take, we have r as a function of theta. So if I take a normal like derivative of that function-wise, I would say the answer would be dr d theta. And so how is dr d theta related to dy dx? All right, let's think about that for a minute. So dy dx, well, here's dx, there's dy, and that's why we call it slope. That's pretty straightforward. Okay, let's think of like what does our dr d theta look like? Well, d theta is a little chunk of angle, so that could be d theta right there. And dr would be a little piece of radius. What's a little piece of radius here? So, you know, if I take this all the way out to wherever it lives, this is r equals f of theta. dr would only be a little piece of the radius. So from here to here, maybe, is dr. Well, it's not area, it's a ratio, right? I'm taking this little length and I'm dividing by that little angle. Right? So this is a little piece of length from here to there, and I'm dividing that by a little chunk of angle. Right? So they're like kind of like incompatible units, right? Here, this is a length, that's a length, they happen to make a slope when I put them together, right? But here, what the hell is that? All right. Well, I can tell you exactly what it is. It's the rate of change of the radius as the angle changes. And it doesn't mean anything more than that. It has no geometric significance. Okay. I mean, it has a little tiny bit. If, and I can kind of illustrate it, oh, this graph's kind of hard to show it on. Maybe I should pick a different one. You could imagine that this is a carnival ride, and in the middle is a little spinny thing going around and around and around. Okay. And then inside that spinny thing is a pulley. And what the pulley does is it pulls you in or lets you fly out depending on what the function says to do. So when theta is equal to 0, you're 1 unit away. Maybe it's a meter. Maybe you're 1 meter away from the center of this ride. And when theta is equal to pi over 12, you're only 0.7 meters away. And as it gets to pi over 6, you're getting pulled into the center, and then you get whipped around the other side, and it lets you out again to a meter, pulls you back in, lets you out, pulls you back in. And what dr d theta means is you're kind of letting, one interpretation of it is you're letting theta move at a fixed rate. So you're always moving around at, like, I don't know, 1 revolution every 2 seconds maybe, like that. And then you're being flipped in and out. And so dr d theta would be the speed at which you're flipping in and out. It doesn't have that much physical consistency. So all dr d theta tells us is how fast is the radius changing while the angle is changing at any point on the graph. So that's the only example I can come up with about what physically is happening. But otherwise, it really doesn't have any use to us. We can find dr d theta all day long, but it's got no physical meaning.
So why did I write this on my paper?
Well, we do derivatives all the time in calculus, right? Are all derivatives meaningful? Answer is no. This one is not. However, tangent lines tend to be pretty important items in a lot of circumstances, right? Wouldn't it be nice to be able to find the tangent line at that point? Yes. Okay, so here's what we need to do next. We need to do 2 things. How the hell do you find tangent slope in a polar system? Because tangent slope is rectangular. And then how do you graph lines in polar?
So are you trying to find the length of a curve?
Nope, that's a totally different subject.
Okay, so what are we doing?
So we're backing up to section 3. Is that right? 11.3? No, 11.4. I skipped over 11.4 where they talked about derivatives. I wanted to do areas first because they're easier. Okay. So polar area, that's oops, that's an H. That's 11.5. So now we're going to back up a little bit into 11.4 and talk about slopes on polar graphs and lines. Come on, pen. There we go. I need a new page. So polar lines first. Polar lines. Okay, we'll start off with a very simple line. Thank you. Stuff for me there. Stuck. Thanks. Okay. Yeah, put your name on there. Okay, so polar line. So we'll start off with a real simple kind of line. Let's just go for the whole thing. Y equals mx plus b is a regular line, right? Okay. Oh yeah, plus. All right, so now we need some kind of relationship that's going to link x and y to the polar world. So that's what we're going to do next. So let's see. I seem to remember that the cosine of theta is equal to x over r, and the sine of theta is equal to y over r. So that means I can say, well, x then is r times the cosine of theta, and then y must be r times the sine of theta. So we can use these equations to substitute in. So that means y is going to be, so I'm going to switch to polar now, rewriting my line, r sine theta, and that's going to equal to m. X is r cosine theta, and then plus b. So all I'm doing is I'm replacing x and y with their equivalents from basic trig. R sine theta for y, r cosine theta for x. Now in polar, we usually write r as a function of theta. So guess what we need to do next? No guesses?
Wait, what was your question?
In polar, we graph things that look like r as a function of theta. So if we want to make a line in polar, guess what we need to do this, to do to that next? We need to get r all by itself, and everything else is f of theta. Go for it. Do some algebra.
And it's sine over cosine.
Yes, it is. Okay, that's up here too now. Fantastic. All right, so you guys do some algebraic wizardry. Tell me what a line looks like in polar coordinates, or in polar notation. You missed some fun stuff, but it's going to get funner. You can do this. We're taking y equals mx plus b, and we're going to rewrite it with x equals r cosine theta, y equals r sine theta. That's this. Now we have to solve for r to graph it in polar, just for fun. Yeah. So we bring the mr cosine theta to the left to get all the r's together. So I think for polar lines, r equals b over sine of theta minus m, the slope, times the cosine of theta. Oops, I think that's what I'm getting. I need some chocolate right about now. I'm all out.
Coffee.
Huh? When's break? Coffee and a chocolate chip cookie would be good. You guys okay with my math or your math? Okay. So just a couple things to note. Compared to the last thing we did, r equals cosine of 3 theta. That was a pretty simple equation, made this complicated curve. On the other hand, a line is a pretty simple thing, but in polar it's got quite a complicated equation, doesn't it? The area, the graph? Oh yes, we graphed that cute thing. No, then we found the area inside of it. Yeah. Okay, so that's a line. So for example, if I wanted to graph the line y equals, I don't know, 2x plus 1, then here that means r would be 1 over the sine of theta minus twice the cosine of theta. Yeah, so all you need to know is, so b goes in the top, m is minus cosine in the bottom, the sine's there. Yeah. Oh, this is an interesting thing though. There's one problem here. What if b is 0? Like there's no y-intercept. The y-intercept is the origin. Is that a problem for this equation? The whole thing's 0. You get nothing. That is a problem. We'll have to deal with that. So here, by the way, just the y-intercept cannot be 0. That's a problem. All right, so let's graph that. Make sure it really is a line. I pointed this out last week, but I don't know if you guys remember. There's an online calculator called Desmos. Good thing I brought it up. Yep. It's at the end of the last recording. And Desmos will do graphs r with theta, but you got to have to type r first. And then I would say r equals 1 divided by, and then I want the sine of, and then you got to hit more to get theta. Remember that more button I mentioned before? There's theta. And then I can go minus 2 times the cosine of theta. And it's just nice because it makes nicer graphs than the TI. The TI is so blocky and awkward. Sorry, TI. But that looks like a lot like the line y equals 2x plus 1, doesn't it? That looks like about y equals 1. Go up 2 over 1. I'm still on the graph. Okay? Looks good.
These lines not go on forever.
Yeah, yeah, so these are kind of, graphing them is a little weird because it's got to sweep the angle out to graph them, right? So what does that mean, to sweep that angle? So, oops, wrong button. So I'm going to graph it here so I can use the trace to see it. Actually, oh well. Yeah, I'm going to use GeoGebra here. It's easier.
The product rule that I know
I had
of,
that moment too.
the product rule that I know of, I was sitting there thinking that's an integral rule. And I was like,
Oh, I didn't
wait a
do
second.
that
No, yeah, but I was just sitting there, I was like,
It's
wait,
not there.
that is the
Shit.
test for doing
though. When do we
it.
get the test back?
Not today. Sorry,
Thursday?
I'm not done. Sure, definitely,
Okay. So
absolutely.
These Manbitch capabilities here.
Hang on, I'm trying to find. Here we go. Polar plot.
I can make a sandwich.
Okay, so I'm just going to put that line in here so you can see how it's graphed. So I want, what is it again? It's 1 divided by parentheses sine of t minus 2 cosine of t. Okay, so there's my line. Now watch how it's graphed here. So here's a equals about 0. And look at how it's graphing in the negative direction first. And then it comes back the other way. So it had to head out over to infinity at some point, right? Because see that point P heading down? Let me blow this up.
Does that come from back maybe?
Yeah, what the hell does that mean?
Circle.
Look at that. Yeah, so this is kind of cool. It turns out if you study enough polar, and we don't really have time to, unfortunately, but I'll just give you the short version. A line in polar is like a circle with infinite radius.
Wait, what? Can you say that one more time?
I can't say that. But the interpretation of a polar line, it's a circle with infinite radius. Yeah. Well, no, it really is a straight line. It is straight. It's just the way polar graphs things. It's weird.
What would that look like if you tried to draw? Just draw what you just tried.
Draw a circle with infinite radius. I have no idea how to draw that, except like this. Because check it out. So it starts off here, and then all of a sudden it ends up on the other side. The point just escapes out to negative infinity and comes back through positive infinity. Even though those aren't places, they're directions.
Okay, that seems impossible.
It does seem impossible.
It moves around from behind the graph, and it's just
That'd be like, that's pretty much a straight line. Because it'll never come back around.
Look at this. It keeps repeating itself. Zoom, zoom, zoom. Isn't that crazy? It's weird. So it's just different, okay? All right. So we'll play with more polar lines in a minute. So we know how to get a line in polar now, except what if the line goes through the origin? B is 0, right? We better take a quick look at that. If B equals 0, then that means y equals mx. Okay. Let's see. What's y in polar? R sine theta. So that means I have r sine theta equals m times r cosine theta. And whoa, what happens to r here? It divides out, right? So then I get sine theta equals m times cosine theta. And anybody want to see the m be by itself? I do. If I do that, then I get the sine of theta over the cosine of theta equals m. Wait a minute, what's sine over cosine? This tells me the tangent of theta is equal to the slope. Hey, wait a minute, don't we already know that? Isn't tangent slope? It is, rise over run, y over x. Yeah. So a line through the origin is just an angle. It is. Okay, right, check this out, right? So let me give you an example from rectangular coordinates. If I asked you to graph the equation y equals 2, what are you going to do? Two, like right here, 2? Oh, horizontally through 2? Like that? Up to, why up to? Oh, why? That's why. So, why do I have to draw a horizontal line again? Why do I have to draw a horizontal line? You're saying it's that horizontal line right there? There's no slope up there. It just says y equals 2. Oh, so you're saying that's really the line y equals 0x plus 2? Oh! Okay. Okay, so another interpretation of this is we've fixed y at 2, but we never said anything about x, so x is free to be anything it wants. Right? So here at this point, x is 1. At this point, x is 2. At this point, x is about 5.573. Right? But at every single point here, y is 2. Okay, so now we're going to go back a step here, and we're going to say that Let's say I let theta equal pi over 4. If theta equals pi over 4, what's m? If theta equals pi over 4, what is m? M is 1. Yes, correct. Okay. So I'm going to graph theta equals pi over 4. Okay. What is r? I haven't stated r, have I? So that means r is free to be anything it wants. Okay. So this is theta equals pi over 4 roughly. Here r is 0. Here r is about 1. There r is about 2. Here r is about 5.573. Or any other value for r. Now you get it? What I was saying? If you say theta is a fixed angle, then you have a line through the origin, through the pole. That's all. So lines through the pole are easy. Theta equals a number. If the line does not go through the pole, then you get this crazy son of a gun to work with.
Sounds like a warm
Okay, next fun part. How do we deal with slope in polar? Okay, now here's the problem I have. Slope m is dy dx. There is no getting around that. That is what it is. Is dr d theta slope? No. It is weird and mostly meaningless. Okay. However, we studied parametric stuff. And theta is basically our parameter for the system y equals r sine theta. And x equals r cosine theta. No. Theta is a parameter. And we studied parametric equations. Now, r generally in polar is some function of theta. So given that r is a function of theta, can you tell me what dy d theta is? If that's y? What rule do we have to use here? What rule do I have to use there? The product rule. Nice job, Anna. Okay, so product rule says take the derivative of the first thing you see, that's r. Well, r is some function of theta. I'm just going to call it r, right? So it's dr d theta. And then leave the second function fixed as the sine of theta. And then the product rule says add on to that, leave the first function alone and take the derivative of the second function. What's the derivative of the sine? It is the cosine. And I didn't leave myself enough space. Let's see if I can remedy that. Almost. Oh shit. Stop that. There we go. Okay. Next thing I need to do is repeat that, darn it, for dx d theta. What's dx d theta going to be equal to? Pretty close. It's going to have a dr d theta first times the cosine of theta minus, yes, r times the sine of theta. And from our work in polar, you may not remember this because you haven't done much homework, most of you, in chapter 11, that dy d theta over dx d theta happens to equal dy dx.
What?
So what that means then is if we take this formula and divide by the black one, this right here is slope in polar. Holy shit, it is horrible, but it is what it is. So dr d theta is cute, but mostly useless. this formula here makes it useful by turning it into what we call slope in Cartesian coordinates, rectangular coordinates. Yes. Well, there are some designs you cannot make in rectangular, right? Oh, you got me here. I'm trying to think of some good examples. Why must we learn this crap? Oh, well, if I'm solving there are some mechanical and electrical engineering problems that I cannot solve in rectangular coordinates. I have to go to polar coordinate system to solve them. Vibrations in a drum head, which relate to lots of different kinds of vibrations. Heating problems that can come up in. Oh, did he really? Okay. So then he's played with polar coordinates, yeah. Yeah. Yeah, because you can really, using polar coordinates, you can really simplify the simple single drum head problem. You're getting there. Okay, so I got a new project for you. You're going to graph this. I'm going to give you a polar function. You're going to graph it, and then you're going to try to find a tangent line on it at a point. Let's see, not that one. This one's a good one. R equals 1 minus the cosine of theta. Yep. And yes, you should write one further out. Yeah, I want the tangent line. Tangent line when theta is equal to pi over 2. I want the tangent line when theta is equal to pi over 2. So I would make a quick sketch of that to see what you're getting yourself into. Graphing utility is highly suggested. I'm going to use my cute little GeoGebra grapher. One minus cosine of t. Okay, and it depends on how you look at it, it's either a sideways heart or a sideways butt. Let's go with butt. Okay. Well, we could make it into a butt if we do I think if we do a sign on there, let's see. Oh, that's the heart. That's what if I do, nope. Ah. Okay, there we go. That's the butt. Right there.
There's the butt.
There's the butt. Okay, but we're not doing that one. We're doing the cosine. Okay. Okay. You said butt. Okay, so there's the graph. If theta equals pi over 2, that's going to put me right up here. I think. Is that right? Yeah, cosine of pi over 2 is 0. All right, so we're going to try and find the slope through that point right there. Guess what formula you need next? That crazy one. Yeah. See if I can get it right without looking. So dy dx is equal to dr d theta times the sine of theta plus r cosine theta all over dr d theta times the cosine of theta minus r sine theta. And this is r, which means we also need dr d theta. What's the r d theta here? Exactly. It is the sine of theta.
That's what I said.
I thought so. Either that or I'm hearing voices. Right? Because derivative cosine is negative sine. Derivative of 1 is 0. All right, so that means we need to fill r and dr d theta into this formula. So we have to replace those buggers. R gets replaced, and dr d theta gets replaced.
That's much nicer. That, I like that more. That's doable. Man, I still don't like it.
Oh, did I make a mistake somewhere? Yes, I did. I'm about to make a mistake.
Yes.
Writing stuff down? Because you're bothering her. Write stuff down. Makes you less bothersome. Yes, it does. Okay, so what do I have here? I've got a sine squared theta. And then I'm going to have a cosine. And I'm going to have a minus cosine squared. Too bad it's not a plus cosine squared, huh? Oh, well. Down below, I have sine, cosine, and I have another sine, cosine. Don't forget to distribute this negative through. That's subtraction, that is. So it looks like I get 2 sine of theta, cosine of theta. Ooh, that's not right. Minus sine theta. Oh, that's interesting. You got to distribute here too.
Oh.
Can you separate out the numerators?
You can factor a sine from the denominator, but there's nothing you can factor from all of the top.
Well, and then separate out sine squared over 2 sine theta plus cosine theta over 2 sine theta cosine.
I can't separate the denominator. You want me to separate the numerator?
Yeah.
And have what as my...
Figure out the cosine on each of the last two.
Oh.
Sine on the first one.
Oh, okay, I see what you're saying. That might help.
Then it is sine cosine minus 1 sine over the top of it.
But then we have another fraction that's kind of unruly. Huh.
Right?
Oh, this is interesting. This right here is the sine double angle formula. Oops, that's not my highlighter. And this is the opposite of the cosine double angle formula. Right? Yeah. So if I rewrite it that way, I could say the numerator then is the cosine of theta minus the cosine of 2 theta. And the denominator is 2 theta. And the denominator is the sine of 2 theta minus the sine of theta. Sine of 2 theta minus the sine of theta. I mean, it's just easier to write. It doesn't make things any better, I don't think. It's just less ink. Do you need to sit up front, Jeff? You heard a ding. Oh, sorry. I'm ding-donging again. Turn that sucker off. I forgot to silence my phone.
She wants to know what trading stuff you did.
How did I do that?
What was the,
Oh, so I recognize that what identity
yeah,
is the so here I have sine squared minus cosine squared. Cosine squared minus sine squared is the cosine double angle. So that means I have the opposite of the cosine double angle sitting here. Right. So there's my negative double angle right there. Yeah. So bottom line is there's a lot of different things. Like Zach had a bunch of ideas on how to reduce this. There's a lot of things we could do, but I don't think it's going to reduce much.
Wait,
Okay. Well, you had one idea that was a bunch of work. How about that? Okay.
that was my fault. I didn't see that 2 in there. I thought that was just data.
I'm saying that most of the time I stop right there.
Really?
Yes.
Awesome.
Because then usually I just want to plug in pi over 2 and see what happens. So do that next. Plug in pi over 2 and see what you get for slope. Yeah, you got to do this. Okay, so I'm going to do it to both formulas to make sure I didn't screw up.
Not answer.
Did you?
0, 0. Yeah, I get 1 over negative 1, which is negative 1. From that one, how about this one? If I evaluate this at pi over 2, I get 0, I get negative 1 in the top, and in the bottom I get 0, negative 1 times, no, uh-oh. Did I do that right? I think I got something backwards here.
Yeah, because negative cosine pi is negative 1 already.
Oh, so it's a positive 1 on the top.
Yeah.
Okay, and a negative 1 on the bottom. Phew.
Oh, yeah.
Okay, which equals negative 1 in general. Good. Phew. I got nervous there. Okay. Yeah, so either way I get negative 1, which is what I was hoping for. Okay,
At least he does.
so what do we know? We know that, where's my graph? This graph right here, at that point of intersection, when theta is pi over 2, r is 1, has a tangent line with a slope of negative 1. Can we graph the line and the curve on the same space?
Probably.
Yes, we can. Okay, so let's do it. So, back to our notes. We have a slope, right? M equals negative 1. What's our point of intersection? Well, it happens when theta is equal to pi over 2. And if we plug that in for r, what's the cosine of pi over 2? So r is 1. So we have the point, rectangular-wise, that is. In polar, we have the point 1 pi over 2. Rectangular. Can anyone tell me what point that is? Oops. Polar, it's the point 1 semicolon. Remember I said use semicolon when you're doing polar points, commas for rectangular. Pi over 2 makes me vertical, right? So that puts me on the y-axis. So y, x must be 0 and y must be 1. I know my y-intercept. So now what you need to do is graph the line y equals negative x plus 1, but in polar form, along with the sideways butt. Go for it. See if you can make that happen. Remember we have a formula for polar lines? Right here. There's the formula for polar lines. We know b is 1 and we know m is negative 1. All right, let's go for it. And I will use the crappy resolution TI because you guys are, sorry to demean your TIs, but they do have crappy resolution. Yours doesn't? Oh, you got the new one?
The back that
Oh, I got to come look at that. I've only seen it a couple of times.
How expensive was it?
That included shipping though, right?
free shipping. Actually, no, I paid for next day shipping because I waited 3 weeks for that when they canceled it on the day it was supposed to arrive.
Ah, from whom?
Someone on Amazon.
Oh,
Eligible.
oh.
As soon as it was supposed to get to my house, they sent me an email saying, "No, we canceled it." Screw it, I got this for slightly cheaper, but it ended up being the same after $3 for next day shipping.
Okay, so I'm going from 0 to 2 pi. My x, I'm going to go from, I think, negative
Lily pad.
3 to, it does look like a lily pad, too. That's a better name than a sideways butt.
What?
Good job.
The name the butt. Now what does it look like? Now what does it look like?
It looks like a half a lily pad because your hand is covered.
Okay, so here comes my lily pad. That's pretty cute. And here comes my line. Hey, look at that. Now, again, the line gets crisscrossed a few times because it doesn't need the whole 0 to 2 pi to be graphed.
Oh.
That's what it should look like, right? We have to have a line tangent to the point when theta is pi over 2 and r is 1, which is right there. I'm going to graph it on Desmos 2 just for fun. Oops, that's not Desmos.
Oh, that's my problem.
Found it?
Yeah,
Are you sure?
yeah.
You have something on your shoulders.
Uh-oh, Desmos couldn't graph that. Oh, I see.
That was a close one.
Okay, so there's my line. And now I have r equals, what is your line?
Oh,
M is negative 1, so it'd be 1 over sine plus cosine.
but I'm using theta, not
Right, theta. Yeah, because we want to see the line. Yeah.
R is polar form.
Yes, r equals stuff with theta is polar form. Correct.
Excellent.
the.
Did you get it, Anna?
I did.
Oh, good. Oh, what did happen there?
I should probably put it in.
Okay, there's the cute little Desmos graph. Look at that. Desmos does a nice job, doesn't it? And it's pretty easy to use. Wonderful. We're out of time.
Woo! Hey,
Darn, we're out of time. Damn. Okay, so you guys have some serious homework to catch up on.